Good morning and afternoon and evening to everyone, and welcome to Ask the Expert, all things SIMS. We are excited to hear from Eurofins EAG's expert, Dr. Charles McGee, Chief Scientist Emeritus. I am Dina Ingram, and I'm the marketing manager assisting with today's event. There are a few housekeeping things to cover before we get started. First, all attendees have been muted. However, if you do have any questions that pop up during the presentation, please feel free to enter them into the questions panel in the bottom right corner of your screen. We have received over 125 questions for this event, so while we may try to answer as many as possible, we will unfortunately not be able to answer all the questions today. So for any questions that are unanswered, those in the questions chatted as well. We will be sending out answers to everybody in the weeks following. Lastly, once the event has ended, there will be a survey that pops up asking you all for feedback. This feedback is very valuable to us as it helps us with like future programming and events. So without further ado, I would like to introduce you to Dr. Alan Wan, who is the moderator for today's event. Thank you and enjoy.
Thank you, Dina. Let me just go through a couple of slides here. You should be able to see before we pass it over to Charles. So let me. So of course, for Charles, he is no stranger to SIMS, which is part of the reason we have him here. Charles brings to us a tremendous amount of experience in doing secondary ion mass spec. Majority, of course, done here at EAG, but even before EAG. Charles has been working on this for over 45 years. He is one of the founding stockholders of the Evans Analytical Group. So not only has he been intimately involved with the technical portions of SIMS, but also with the company in general. So by all means, it is our pleasure to have him here today. Just to go over today's agenda, we would also like to introduce to all of you who are not familiar some of EAG in general, as well as our SMART chart, which is a summary of the different techniques and services that we offer. But more importantly, we also want to be able to have time for your questions, which you had submitted earlier to us, and we'll try to select a few, if not have most of them covered also by Charles' talk. So EAG is a global leader in analytical services for surface analytical techniques. A lot of our labs are located in the US. So you can see many of the orange dots, which represent our lab locations, are located in US, many of them also in the state of California. But we also have laboratories throughout the world. We recognize that it is a worldwide business, and so hence we do support in many different regions. And so we have over 600 highly educated employees spread out across 20 different locations. And we do service, quite literally thousands of different clients in many different countries. So we recognize that, again, the materials characterization needs are worldwide. And the SMART chart, which is, this is a nice summary of all the different services that we cover in EAG. Some of you who are familiar with us are familiar with this diagram. It covers analytical spot size as well as the detection limits or detection range. So going from either scanning techniques or imaging techniques, for example, which are primarily only for imaging and not necessarily for elemental analysis, but for other techniques as well. And in particular, we will be talking about today dynamic SIMS. So dynamic SIMS, of course, is depth profiling SIMS, covers a significant area on this chart, which that represents a very good detection limit, a good spot size. These are both in combination can be used to provide a significant amount of elemental information, especially in the depth profiling mode. So also when you are choosing a technique, it is important not only to consider the spot size as well as the detection limit, but also the overall depth of analysis. And so we do also like to point out here, we have an arrow representing SIMS. this really is there to show you that we can tune the SIMS to do something very shallow. So we could use low energy bombardment to focus really only on the top few layers, all the way up to using high energy bombardment to do even quasi bulk like or really bulk characterization, really drilling into the deep depth of material. So either way, this type of analytical depth is particularly important when choosing a technique for the problem you have at hand. So without further ado, let me pass over to Charles.
First, I want to thank you all for submitting all these questions. They're very good ones, ranging from the fundamentals of secondary ion mass spectrometry to really some of the nitty-gritty questions in how it's done and in data reduction and how to read the depth profile plot. So to answer those wide-ranging questions, I've put together a few slides, and each one will address some of the questions that you have asked. So what applications do we have in SIMS? The key applications are dopant profiles in thin films. We do lots of ion implantation profiles, contaminants in thin films, thin film layer structure, thin film thickness, interface contamination profiles, thin film composition in limited cases. The materials analyzed are semiconductors, thin film, dielectric films, metal coatings, metal films and coatings, and I will throw in there everything else. I have analyzed everything, including the kitchen sink. I have analyzed porcelain kitchen sinks before. So it's a very widely applicable technique. Here's how it works. We have an ion source on the left, which bombards the sample and erodes the sample, so the instantaneous surface from which the particles are emitted recedes into the bulk as the analysis proceeds. And the sputtering will cause positive ions, negative ions, and neutral atoms to be ejected. And I want to stress that by far and away, most of the particles that are ejected are neutral, and they are unavailable to us because it's a mass spectrometric technique. We have to have ions. So then the ions are passed into a mass spectrometer and into a detector. And we can display the data in three different ways. A mass spectrum, which for reasons I'll explain in a bit, is not used very often. An ion image there at the bottom, we can get a mass-specific XY image of the sample surface. But the most common is to do a depth profile. We follow one or more elements of interest as the sputtering proceeds. And since as the sputtering proceeds, the surface recedes into the bulk, if you plot the intensity versus sputtering time, you will get a depth profile. That's the really basics of SIMS. Everything else is I won't say window dressing, but it's where the complications set in. There are three different types of mass separation. We have the magnetic sector instrument over here, the quadrupole mass filter, and the time of flight. Common to all of them is a primary gun here to bombard the sample. And the ions are extracted from the sample here in this magnetic system. They're energy analyzed, and this magnet really separates the ions according to their mass to charge ratio, and then the ions are detected. Same with the quadrupole, except the ions are extracted this way, energy analyzed, and now instead of a large magnet, we do the mass separation with a quadrupole mass analyzer. In a time of flight instrument, this is basically, just very different. We have a pulsed ion beam, we have pulses of ions, and when a pulse of ions hits the sample, a burst of secondary ions is emitted, and these ions are accelerated and travel in this path with these electrostatic sectors. And all the ions have the same energy. So the lighter ions travel faster than the heavier ones. So if you simply time from the input pulse when the ions are made until when the ions hit the detector, you can calculate the mass. Now, these three types of instruments have strengths and weaknesses. The magnetic sector has high transmission and high mass resolution. The high mass resolution allows us to resolve many mass interferences, which are very common in SIMS. But it has a weakness that the primary beam angle, which is fairly important, is dependent on the primary beam energy, and it also is very difficult to bombard with a very low energy ion beam with a magnetic sector. The quadrupole mass filter has low primary beam energies, can go as low as 100 volts. And the primary beam is independent of the beam energy, but it has low mass resolution. We have no way of resolving any mass interferences, and it has, I won't say low transmission, but certainly lower than a magnetic sector. Time of flight has high transmission, high mass resolution, excellent lateral resolution, parallel mass detection. It sounds like, oh, that's the perfect SIMS instrument. But quantitation is somewhat difficult, and depth profiling is limited because the pulse nature of the primary beam does not really erode very much of the sample. You have to have a separate ion gun to erode the sample that is different from the ion gun that creates the signal. And people have questions were asked, what kind of samples can you analyze in a SIMS machine? What kind of sample prep is needed? How big can they be? Well, here's an extreme example. It's a 19 millimeter steel ball bearing that I was able to analyze in a quadrupole SIMS machine. You could not analyze this kind of sample in a magnetic sector or in a time of flight because of the extraction field and the curved surface of the sample. It just wouldn't work. Plus, you would never be able to have such a high sample in either of those instruments. But with a quadrupole, no problem. So in a depth profile, many of you ask, well, what is a depth profile? How does it work? So if we have our primary beam here, sputtering the sample and digging a crater, particles, positive and negative ions are being emitted. And since the surface is still in material A, we have a profile for A right here. If you sputter a little further, until the surface reaches this interface layer of X, now we start to get a signal for X. And as the profile goes further, the X goes down and we're sputtering in the B layer until we hit the substrate C, and then the B layer goes down and the C comes up. Sounds pretty simple, but many of you ask questions on, well, what happens at the interface between layers? People have said, well, it's impossible to quantify things at interfaces. Well, it's difficult, I will admit that, because right here we do not have material B and we do not have material C. We have some mixture of the two. And as I'll show in a minute, all of our quantification is based on standards, and they would be in material B or C or A, but we don't have any standards for this mixed unknown composition here at the interface. So the question was right to be asked. Quantification at interfaces is difficult. Now, the primary beam is very important, and people ask, well, how small an area can you analyze? Well, it's depending on how small the primary beam is. We can have beams as small as 2 microns or as big as 50 to 100 microns. But we raster it in this square pattern. But the size of the beam is indicated by this circle here. And as the crater gets smaller with respect to this gated area here, And this area here is where the detector pulses are only counted when the sputtering beam is hitting this center part of the crater. Because this is going to be the flat bottom of the crater, and we don't want to see things on these crater walls because that's at a different depth. But it's difficult to shrink analyze the sputtered area down very close to the gated area, because then the sloping crater wall will start to overlap on the gated area. Now, we have analyzed, I have analyzed personally a sputtered area as small as 20 microns, and the analyzed area of less than 10. And the magnetic sector instruments out in California, we had a total sputtered area of about 10 microns with a detected area of 3 to 4 microns. So, or, well, let me say that SIMS, stress that SIMS is a sample limited technique. You can't shrink the beam, the crater, the gated, the analyzed area as small as you might want, because we can only use every atom in this area once, unlike Auger or XPS, which can continue to irradiate the samples, the atoms in the sample, and get signal repeatedly from those atoms because they remain in the sample. In SIMS, we sputter those atoms off, so we can only use them once. So if you shrink this gated area too small, there won't be enough atoms there left to give a usable signal, because remember from the previous slide, most of the sputtered particles come off as neutral atoms. We played some tricks to make as many ions as we can, but you can't make the analyzed area basically infinitely small. You run out of atoms. So here's an example of a quantified depth profile. It's a sample of silicon germanium on silicon, and this cap layer is undoped. We have a silicon germanium ramp and carbon doped silicon germanium here and here. And I show this because people ask, well, can you analyze semiconductor basically compounds or areas? So can you analyze something that isn't just silicon? Well, certainly we can. Again, as we'll get into in a minute with quantification, the silicon germanium layer requires different quantification than the silicon, because the sensitivity of boron and carbon is different in the silicon germanium layer. And the sensitivities can be really drastically different. This is a plot of the relative positive ion yields from pure elements. Excuse me. And you can see that the sensitivities vary by orders of magnitude. This is a log scale over here. So we're changing by 5 orders of magnitude. So we need standards for all these different elements because they all have vastly different sensitivities. And as I was alluding to in the previous slide, if that wasn't bad enough, each element would require a standard in each different material. This boron here would require a standard in silicon and a standard in silicon germanium. And we have to have ways of providing accurate quantification as we cross from one layer to the next. So and people ask, a number of questions were asked. Well, why is SIMS so difficult? Why is it so complicated? Well, this slide is the answer. The element sensitivities are so different across the periodic table. A question was asked, well, how is SIMS different than glow discharge mass spectrometry? Glow discharge mass spectrometry has very uniform sensitivities across the periodic table. That's because the ionization mechanism does not occur from the sputtered surface. It occurs by a pinning ionization process with an excited argon atom. And it has very uniform sensitivity. Not so with SIMS, and that's the root of most of the problems. So Here's how we can get around that. We have a primary ion, the purple guy. He comes in and gets buried in the sample and ejects some particles, ions, positive and negative ions, but mostly neutral atoms. And here we have some dopant atoms here. And there are a number of things we want to point out, because people have asked, well, what about the depth resolution between SIMS and, say, XPS? Well, XPS has an escape depth of about 25 angstroms, and there's and that's a 1/E depth resolution. SIMS is kind of depicted there. Most of the detected or sputtered atoms are emitted from the top 1 or 2 monolayers. So it has really good sensitivity that the inherent physics of XPS can just not match. But the primary particle becomes embedded in the sample, and as the surface here recedes into the bulk, magic things happen. The primary beam is implanted into the surface, and ionization only happens as the sputtered species leaves the surface. So there's a competition of electrons from the sputtered particles, and you can think of with oxygen bombardment, we can increase the fraction of sputtered particles that form positive ions if we bombard with oxygen, and decrease the number of free electrons that are available to neutralize a leaving positive ion. And if we can bombard with cesium, and we can decrease the electron affinity of the surface by bombarding with cesium and increase the number of free electrons available to attach to a leaving atom. And remember, there are lots more leaving atoms than there are ions. And these two, some would call them artifacts, are responsible for why we do SIMS in the first place, because these two processes increase the sensitivity of SIMS by between 3 and 4 orders of magnitude. Without this enhancement, say if we bombarded with argon, our sensitivity or detection limits would only be marginally better than those of XPS and Auger electron spectrometry. It's because of these enhancing bombarding species that it works. And again, that's another complication by SIMS. People ask, why is it so complicated? Because you have to decide whether to bombard with cesium or oxygen and what kind of ions to detect. It requires a lot of experience to determine how to do this the best. The blue atoms, elements in the periodic table here are optimally analyzed with oxygen bombardment, and the light yellow elements are best analyzed with cesium bombardment with negative ion detection, and the yellow ones, including most importantly the inert gases, can analyze by sputtering with cesium and then analyzing a cluster of cesium plus attached to a leaving neutral. And I show this because many people have asked, well, how many elements can I analyze at the same time? Well, theoretically, almost unlimited. If you have a quadrupole instrument, you could switch masses very quickly. But you can't really analyze with optimum sensitivity the blue elements and the light yellow elements, or these elements, and the same analysis. We can do them all, but not in the same analysis. They will have to be analyzed multiple times. So that's why I show this. It's very important. And again, why is SIMS so complicated? It's because of the ionization, and you can't analyze all elements at the same time like you can with XPS and Auger. SIMS must be quantified using a standard of the same elements being analyzed in the same matrix as the unknowns. The standard must be analyzed under the same analytical conditions, and generally we analyze the standard, well, always we analyze the standards right alongside the analytical samples. The accuracy of SIMS is determined by the accuracy of the standard. Now, full stop, please understand this. The precision of SIMS can be very, very good. It's not a standard SIMS is probably good to 5%. but the accuracy of the analysis is going to always be determined by the accuracy of the standards that you use to quantify the results. Fortunately, the National Institute of Standards and Technology has boron, phosphorus, and arsenic with an accuracy of 1%, 3% for boron. But you can use ion implantation to make reference materials with an accuracy of plus or minus 15%. But we at EAG try to verify the accuracy of these implanted reference materials that we have made by using some other ancillary technique. But it gets really sticky with 3,5s. Again, why is it so complicated? If you have dopants here, tellurium, zinc, silicon, carbon, an impurity of oxygen, you want to analyze all of these in 3,5 structures. Well, it's not just gallium arsenide or indium phosphide or gallium nitride. You have all of these mixed stoichiometries. So you need standards for all of these, And to make matters worse, the starred matrices can come in a myriad of different stoichiometries. So you really have to have a standard for everything. Now, one of the questions that was asked in the write-in was, I want to analyze for oxygen in aluminum gallium nitride, and I have a standard of oxygen in gallium nitride, and I have a standard in aluminum nitride. What do I do? The answer is standards, standards, standards. I'm sorry to make your life difficult, but you have to have a standard made in the algan composition in which you're working. I looked at our database, and we have 30 separate standards of oxygen in aluminum gallium nitride over a range of different aluminum concentrations, different oxygen doses, different oxygen energies, even different oxygen isotopes. So that's why what has led EAG to collect between 6,000 and 7,000 ion implanteds and other bulk standards. You just can't do quantification without standards. So accuracy, the standards we're talking about determine accuracy, and you can read the definition. The accuracy is the extent to which a given measurement agrees with the true value. Precision is the extent to which a given set of measurements of the same sample agree with their mean. And accuracy and precision are different. They are independent parameters. And I'll show you how that works over here. We'd like to have a low spread of bullets in the center of the target. That means the precision is very good and the accuracy is very good. But we can have good precision in SIMS, but if the standard is not good, then they will not reflect the true value. They'll be closely grouped, but off center. You can have low precision, but high and poor accuracy if they're widely grouped and not in the center. Or you can have poor accuracy, poor precision, and good accuracy. This is what we strive for, but if your standards are not good, this can happen. So how do we do standards? How do we make standards? This is an ion implanted standard here of 200 kilovolt phosphorus implanted into silicon and has a Gaussian shape. And you can determine the sputtering rate. You can transfer sputtering time into sputtered depth if you know this depth from a previous analysis or from the tables that you've done. Or you can measure the crater depth. Here's a AFM scan of a sputtered crater. And you can run the profilometer tip over here and measure the crater depth very easily and transform sputter time into sputtered depth. Now, there's a problem with some kinds of samples where it's not a homogeneous sample. This is easy. This is all silicon. But in the silicon germanium sample, we saw that some of it was silicon and some of it was silicon germanium. And they have different sputter rates. So you have to have ways of compensating for that by measuring the rates of the different materials independent. I want to point out something here. Many of you have asked about artifacts. How do you know what an artifact is? Well, this particular sample here, this phosphorus peak here, is right at the surface, and phosphorus has a mass interference with silicon plus hydrogen. So this is an artifact. And if I were plotting that and giving it to a customer, I would put a little message on the plot that says artifact with an arrow pointing to that peak. Because the customer, you guys, are not going to really know whether that's an artifact or not. Here's the silicon germanium I was talking about the sputter rates of this. It's going to be different from the silicon here. Also, another artifact, so there are lots of artifacts in SIMS, especially at the surface. This oxygen here is from atmospheric contamination. So this high oxygen at the surface is probably not really in this cap. It's really on the surface layer, and it's being driven into the sample by the action of the sputtering beam. Likewise, this boron is undoubtedly not real. If you have any sample out in air and expose it to room air, the surface will get contaminated with about the mid 10 to the 12 per square centimeter of boron, always. So that's probably, well, undoubtedly, that's an artifact. Another big artifact is matrix effects, and that is the difference in sensitivity of one element in one matrix versus another. And you guys have asked many questions about matrix effects and what we do about them. That's an implant in a simple arsenic implant in silicon. It has the anticipated shape. If you grow an SiO2 layer on it and put the same implant through the SiO2, you get this totally ridiculous profile. And that's because the ion yield of arsenic is much, much less in the SiO2 than in the silicon. We have ways of calculating this, have standards of arsenic and SiO2, and we have some mathematical modeling ways so that we can meld together the sensitivity in oxide and sensitivity in silicon and get more or less a smooth curve. But the sensitivity difference here is so great that it's hard to completely remove the artifact. But SIMS is certainly subject to artifacts where the sensitivities of the elements are very different between the layers. So I have some analyses here, examples, and all of these pertain to the questions that you guys have asked. Here is an analysis of simple boron implant into silicon, and I show this and this to show detection limits. People say, well, what kind of detection limits can I get? Well, this is about, this and this, well, all of them are about, these two are 5e13 per square centimeter. Silicon is 5e16 per square centimeter. So this is 1 part per million atomic. 1, 2, 3, this is 1 part per billion atomic. And down here, we're an order of magnitude less, and that's 1/10 of a part per billion atomic. The center one shows the difference if you implant the phosphorus, in this case, along a channeling direction, so the phosphorus atoms kind of sneak along in between the rows of silicon atoms. You can get an anomalously deep penetration. The SIMS can see that. So 3-5 layer structure profiling. Development and monitoring of epitaxially grown layers to greatly benefit SIMS, and we can determine layer structure, dopants, and all these good things, and a lot to help with process development. Here's an example of an indium phosphide heterostructure bipolar transistor where we have this structure over here. And we can monitor the major elements, the gallium here, 2 different gallium levels are here. When you get to the indium phosphide, the gallium drops off. Carbon doping here and here, and silicon doping here, and this top layer here is the INGAP. So it's an example of looking at major elements. But in this particular case, the major elements with the right pointing arrow are not quantified. They're in counts per second. But I'll show you some later where it is quantified. We can also follow trace impurities, oxygen and hydrogen. And people are asking a lot about the detection limits of atmospheric contaminants in these layers. And they're very important, but they're a problem because these elements are contained in the residual gas in the vacuum system of the SIMS machine, and they're continuously contaminating the surface as you're sputtering it. So the best way of reducing these background levels is to have a very low pressure in the vacuum chamber. But here, if I was giving this plot here, I would have to say that I label this level here as detection limit if I had previously determined that it is. It's very important to not lead people astray as to what's real and what's not. Charge compensation. Lots of people have asked about, well, how do we, can you analyze insulators? And how easy is it? I can answer that, difficult. And how do you do it? You have an ion beam here, positive ions, and we have an electron beam coming in here, and it creates low energy electrons from the sample surface that get sucked over to where the primary beam is hit. Sounds straight, easy enough. But oftentimes we're looking at low K dielectrics or SiO2 layers that are not thermal, they're put down, they're deposited. And the electron beam, if you're not careful, can actually damage the insulating layer that you're trying to analyze. So you have to be very careful with the electron beam parameters to not cook the layer of interest. Low K dielectrics are famous for this, very difficult. But here's an analysis that we can do with charge compensation. It's a failure analysis of a chip. It's from a 100 micron area on a chip that was had the plastic of the package removed in fuming, whatever it is that they use. The wires for were still connected to the bond pads of the device. So we really didn't have to do anything more than just take the plastic off. And we see we have a nitride here. We have an SiO2 layer here. But I know it's a silane oxide because these are TiO oxides, and we follow carbon, and the carbon goes up. Remember, this TiO is tetraethyl orthosilicate as a starting material. So some of the carbon gets incorporated into the film. We have a TiO BPSG here, so we follow the boron and phosphorus levels here. Another oxide, polysilicon layer, oxide here, and then the substrate. We have spikes of aluminum. This is where the metallizations were done. In this particular guy right here, we see a lot of sodium and potassium were introduced. And it happened that we learned later that the photoresist that was used at this step was contaminated with high levels of sodium and potassium. And these were driven in when the plasma etching was used to remove the aluminum. They changed resist, and we analyzed some more, and this problem went away. So this is analysis of charge compensation, mobile ion analysis. These are very difficult to analyze without moving them. And there was one question about, can you analyze lithium? It's very light. It has miserable sensitivity by any electron spectroscopy technique. But by SIMS, it's quite sensitive. It's an alkali ion, and I just didn't measure it here, but I certainly could have included lithium in this analysis. And our standard actually is an ion implant standard in SiO2 of lithium, sodium, and potassium, all in the same sample. So failure analysis, this was a great success. So you talk about analysis of alloys. In this case, a semiconductor alloy, and this is a real great case. We analyze a vertical cavity surface emitting laser, and it's made of a whole bunch of algas layers, like 100 of them. And we are able to quantify the aluminum levels in these layers thanks to another NIST standard. NIST has an aluminum gallium arsenide certified reference material. Actually, they have 2 of them. And using that, we quantify the aluminum concentration in all these layers. But we measure the carbon doping and the silicon doping. And this is the P-type Bragg reflector, and this is the N-type. But we can also measure the carbon impurities that come in with the silicon. And here we have a carbon detection limit in the last gallium arsenide layer, and it's in the mid E15 range. And same with oxygen, it's also in the mid E15 range. But to do this, the vacuums, the machines that do this are about in the mid to low 10 to the minus 11 torr region. So it's a challenge. So SIMS is often tried to evaluate diffusion in metal layers, and analysis of good depth resolution is 2 factors working against it: roughing and ion beam mixing. But strategies can be used to reduce these. And here is the killer of killer samples, where you have to sputter through a polycrystalline layer, and you're trying to see if the copper gets through to the silicon. And if you analyze from the front, you can see that you get very bad roughening of the sample. So the surface is simultaneously in the copper and in the tantalum nitride. And as the sputtering continues, it will be really bad. So the copper here, it looks like it's gone into the silicon, but you have to ask, has it really? These are, in this particular analysis, these are artifacts. And if you didn't do what I'm just going to show you in a second, you would have to mark these as such, mark those as artifacts. What can be done? We can simply turn the sample over, because silicon does not roughen when you sputter it, and you leave less than a micron of the backside silicon left by polishing it, and then you sputter through that with no roughening, and you get a beautiful profile here of silicon, tantalum, and copper. And you can see from this, where we have no roughening, the copper really has not gone into the silicon. The tantalum nitride has acted as a great silicon, as a great copper diffusion barrier. I think this is my last example. Many of you ask, well, can you analyze polymers? Yes, we can. Here's a spin coat of deuterated polystyrene and polymethyl methacrylate, diblock copolymer spin cast onto silicon. This is as deposited. And again, it gets to the idea many of you ask, well, can you analyze isotopes? Because the other surface analytical techniques cannot. Well, SIMS, being a mass spectrometry technique, can certainly analyze isotopes. So here we have the hydrogen profile and a deuterium profile. And after annealing them at 170 degrees for a few days, you can see that the causes the block copolymer to separate into individual layers. And the deuterium peaks represent the profile of the polystyrene, and the hydrogen represent the profile of the PMMA. So pretty slick. And we did a lot more analyses like this years ago. So isotope analysis, polymers, insulators. I won't say no problem, but it certainly can be done with a little practice. So strengths. Excellent detection of dopants and impurities, depth profiles of layered structures, detection of all elements and isotopes, including hydrogen, stereochemistry in some applications. Limitations, it's destructive. We do put a hole in the sample. Very specific standards are required. That's a huge limitation. Element specific, it's a poor survey technique. If you don't know what's on the sample or in the sample, it's best to try to use something else. However, you may be stuck with SIMS, because SIMS, among the surface analytical techniques, is the only technique, as shown from the smart chart, that will have a sensitivity of less than 0.1 atom percent, which is kind of where XPS and Auger run out of steam. So that's the reason you use SIMS. Despite all the problems and limitations and things, it's sensitivity. That's why you use it. And I want to point out here at the bottom, because we're sputtering and tearing up the sample, there's no chemical information available with depth profiling SIMS. And many of you ask about that. Sorry, can't give it to you.
Thank you very much, Charles. And so we have time now to actually address some of the questions that were asked from the general audience. I will actually try to ask a few of them now. First question I have here is, can you explain interface effects in SIMS? I'm told impurity concentrations at air film and film substrate interfaces are non-quantitative and would like to understand why.
It goes back to the difference in sensitivity between matrices. The surface of a sample, almost any sample, is going to be highly oxidized, and the oxygen for positive ions will enhance the sensitivity. It may affect negative ions also. It also has a lot of carbon, oxygen, hydrogen, and nitrogen impurities on that surface, so it's often difficult to quantify what's really underneath all the crud. And I addressed a little bit before at interfaces between layers or interfaces with the substrate. If the layers are different compounds, the elements of interest will probably have different sensitivities in those different layers. And it's incumbent on the analyst to try as best one can to use appropriate standards to determine the sensitivities in those layers, and by some judicious plotting techniques try to avoid large discontinuities in the plots between the layers. But if if you have an epitaxial film grown on the same substrate, gallium nitride on gallium nitride, then there the materials are the same. So there, if you see a peak at the interface, that peak is going to be real.
Thank you, Charles. And then next question. Could you please comment about SIMS versus EDS?
Okay. EDS, a very powerful tool. It's used mostly for major element analysis, mapping, or line scans. It's not very often used for quantitative analysis because EDS really doesn't use standards. You use kind of tables of sensitivities or relative sensitivities. But SIMS uses standards. So we can oftentimes be quite quantitative in these same kinds of samples. But I want to draw a difference between EDS and WDS, which is wavelength dispersive spectrometry. WDS does use standards. Instead of using a silicon surface barrier detector to determine the energy of the electrons, you use a crystal spectrometer. And the WDS can be very quantitative. We often use WDS to quantify some of our standards that we use in SIMS. So EDS, basically no standards, and SIMS standards. But if you don't have standards for SIMS, then you can be telling huge lies, like orders of magnitude. So you have to watch it.
Wonderful. Next question. Can SIMS quantify the release of low Z elements like hydrogen and helium?
Okay, I've showed you some hydrogen profiles. We can certainly do that. You have to have a very good vacuum to do that. Helium is difficult. It's one of those inert gases that on the table, periodic table I showed, has to be analyzed. Well, you can't analyze it as an atomic negative ion. It has a 0 electron affinity. It will not make an atomic negative ion in the ground state. As a positive ion with oxygen bombardment, it's miserably insensitive. You could go back and look on the sensitivity of the elements versus atomic number. It's because it has a very, very high first ionization potential. It's hard to pry that electron off, so it doesn't ionize very well. But what we can do is bombard with cesium and look for the cluster ion of cesium attached to helium. And that gives kind of okay sensitivity. It's not going to be great, but it's about all we have.
Okay, time for a couple more questions. Other than determining mill rates, what compound specific details are required to develop a characterization model?
Characterization model. Let me answer that by saying that SIMS, I think, is the ultimate empirical technique. There are really no models. People tried to model ionization sensitivity, ionization efficiencies back in the early 70s, and it was a disaster. People really don't try to model things in SIMS. It's all based on measurements. It's measured standards, measured sputter rates. It's just all empirical.
Okay, interesting. Next question was, how can you know or anticipate where the results are being skewed by matrix effects?
If the matrix difference, you're not going to get a matrix effect in the middle of a layer of homogeneous composition. If you see spurious spikes and strange things that you can't understand, can't predict in the middle of a otherwise homogeneous layer, then those are not matrix effects. Matrix effects come when the matrix in the material changes from one layer to another. And then you have to, the analyst has to have a good understanding of how different those matrices are. We have different matrices of 3,5 compounds, but say all the arsenides are not drastically different. So there are very few matrix effects between arsenides. But if you have well, with the exception of aluminum gallium arsenide or aluminum gallium nitride, the addition of aluminum will affect some positive ion yields. And you just have to recognize that and steer clear from those analytical conditions that create the artifact. Increasing aluminum increases the sensitivity for positive ions. So I've been bitten by that several times. For instance, magnesium and gallium nitride and aluminum gallium nitride. The aluminum increases the magnesium sensitivity as an atomic positive ion, so we don't do it that way anymore. We do it as a cesium cluster ion, cesium attached to magnesium. We just have to recognize when you're liable to have the matrix effects.
Okay, we have time for one last quick question.
It's going to be a doozy.
What is the spot size of the primary beam? What sort of resolution can you get when analyzing an area with SIMS?
Well, if you have a time of flight machine, they have a liquid metal ion source, and they can make a considerably submicron ion beam. So you could analyze areas of a small number of microns. We have analyzed areas as small as 10 or 12 microns with a magnetic sector instrument. I have analyzed areas as small as 20 microns. And a rule of thumb is that the primary ion beam has to be at least 5 times smaller than the rastered area that you're looking at. Otherwise, you're going to have what we call crater edge effects. But remember, as I said, the smaller you make that detected area, the fewer number of atoms you have. And if you have a really low ion sensitivity element, say like cadmium, it's going to be detection limits will be unusably high because we have fewer atoms, and each atom has a very low probability of ionization. So we can make small areas, but we can't necessarily get useful data from them. Remember, SIMS being a sample limited technique, you want to analyze as big an area as you can with as much current as you can, commensurate with the data point density that you require in the analytical area that you have.
Thank you so much, Charles. I will spend the last few minutes to wrap up some things. So again, I thank you all for attending our event. On the next page, sorry, going down. Sorry. I'd like to wrap up with a few comments. Again, why would you like to come to us for services? Certainly EAG has a reputation for being good at client confidentiality. It's essentially the core of what we do. We essentially enter non-disclosure agreements essentially with every client, every job. We're established throughout science as leaders for what we do for a wide variety of techniques that we do. So of course, not just for SIMS, but for many other techniques that are required for the complex problems you have. So with that, we have extensive knowledge base. Can also offer multidisciplinary. There's no magic bullet when it comes to commercial surface characterization. Different techniques have different strengths, and by utilizing more than one technique, we can actually get more information on the problem you have. We can also scale. So also we have a significant amount of instrumentation. As they stated here, we have over 2,500 instruments. This allows us to scale our operation to what you need. So in the case you have to do a ramp up, you have to actually bring multiple tools online over a period of time. We have the capabilities of being able to meet that demand. And so also, and your time constraints as well. In order to be timely, you have to have capacity. And so in the business, we have a significant amount of capacity for what we do. We're also a global leader for various testings of materials, not just also for characterization, but also the evaluation of passing certain criterion. And of course, being part of the industrial consortium, we are also ISO 9001 and 17025 accredited, which is also a requirement in some cases for certain businesses. So either way, we have what you need for many of your problems. So we certainly would love that you can still continue to reach out to us. And so I think there's a little bit of wrap up. I believe Dina wanted to talk also about upcoming webinars and maybe a few other aspects.
Thank you, Charles and Alan, and thank you everyone for attending today's Ask the Expert webinar. If we didn't get to your questions today, we will be following up with you soon. If you have any other questions, please send in your questions to the email address on the screen. I've also placed it in the chat as well. And again, once you leave today's webinar, a survey will pop up, and it is our hope that you would please fill this out, as your feedback is very important. We have 3 other webinars upcoming this next month, so if they are of interest to you, please do register. I have put the link also in the chat for that as well. And on behalf of Eurofins, EAJ Laboratories, and our expert today and moderator, thank you for joining us, and have a great rest of your day.